And as I start, for those of you who don't know me, I'm Irina Gaynanova. I'm associate professor in the Department of Biostatistics in the School of Public Health. I'm a relative newcomer to the University of Michigan. I've been here for 2.5 years. Before that, I was in the Department of Statistics at Texas A&M. And I'm a statistician by training, so I'm a quantitative science. I have very deep passion for diabetes research that brought me to continuous glucose monitoring data. And I worked with that data for, I think, almost 10 years at this point, and that's my primary area of expertise, although I do a lot of other work in the wearable device as well. And what I hope to do today is give a broad introduction, whether you're familiar with CGM technologies or not, give you a little bit of a tutorial on how you can analyze this data, and then conclude with some more recent directions. And as I told before, Victoria, feel free to interrupt me at any time during my talk. Feel free to ask questions, and I'll try to get us on time. With that, so as I said today, the objectives are, what is the CGM data? What are the contexts of use? I'm gonna show you how to visualize the data and do some calculations of common metrics using the package that I have developed with my group called iglu. And then I will finish with the broader CGM research perspectives. For those of you who like to follow along, so the package is in R, and I will have all the code base in the slides that we're going to use. If you are not an R user, there is a link over here to the Shiny app, and I have it preloaded right here. I just need to update it, fall asleep. So basically, this is a web-based graphical user interface. It is free and open to the public. It has an example data from 5 subjects that it comes from, and it's just point and click for various plots and metrics that you can try as I go along. All right. So let me start with what the CGM is. So it's a small wearable device. Here there is a Libre CGM. This is a Dexcom G6. It goes on the arm. It has a tiny needle, and it measures interstitial glucose levels, typically every 5 minutes. Dexcom CGMs last for 10 days, although they're working towards a 15-day meter, and Libre lasts for 14 days, and they're also working for a 15-day meter. So basically, you put one on, you wear it. Once it expires, you trash it, you get a new one, and put that one on. So to kind of understand why we need this glucose meter and measure it so often, let's think a little bit, what does the normal insulin glucose levels should look like. And this is a cartoonish illustration of a person without diabetes, where as we eat, we have breakfast, depending on what we eat, our glucose will go up. Our body will sense that our glucose goes up, will produce insulin, and then it goes down, and then we eat again, and this process happens. You can see that glucose in US typically reported in milligrams per deciliter. The normal range would be somewhere 70 to 120. In Europe, the unit of measurements is typically different. Everything that I will do today will be milligrams per deciliter. This is a very cartoonish illustration because it changes a lot depending on when we eat, what we eat, whether we exercise or not, whether we have stress, how well we sleep, etc. And traditionally, when we think of glucose control, the standard biomarker is hemoglobin A1C or HbA1c, which represents average glucose levels for the past 2 to 3 months. And clearly, just one number representing the average is not going to capture this complex relationship that we see. And when there is any kind of dysregulation, whether it's type 1 diabetes or prediabetes, then things get a lot more complicated. So this is an example CGM data that comes with our package iglu. It's an older device, it's a Dexcom G4 measurement, but they're still representative. It is a subjects with type 2 diabetes that is not on insulin. And what you can see here is that the horizontal red lines correspond to 70 and 180 milligrams per deciliter. This is the typical target range that I'll come back to. And you can see that there's a lot of excursions. They go pretty high. It's having some missing data here and there, which is also pretty common. And this is the data where we don't really know what they ate or when they ate, but lots of different trends that we can gain from this. So how does the CGM data gets used? Some of the context, oh, sorry, went too quickly. Here we go. How is the CGM data used? So the most common one, or used to be at least, is the diabetes management. So people who have type 1 diabetes, they use CGM data to inform insulin usage. With type 2, those who are on insulin can also use it to inform insulin usage, but a lot of times they can use it just to inform their own dietary choices and behavior by reacting to the measurements that they see. Of course, within the clinical context, when people with diabetes go to their clinicians, typically it's an endocrinologist who would review the data and decide whether the treatment adjustments are needed or insulin dosage adjustments. And increasingly, CGM data is being used in clinical trials with CGM-based outcomes to evaluate treatment efficacy. But I think there's a lot of potential for research at large. There's a lot already that's been done, and that I think there's some new opportunities as well. So within diabetes still, there is a lot of interest in artificial pancreas systems where CGM data can be paired with insulin pump in a predictive model to optimize insulin dosage based on the predicted glucose values. But as we get more larger scale data, we can also look at the retrospective associations between CGM-based measures and various patient characteristics, for example, the age or lipids levels and so forth. We can look at the effect of nutrition and different diets on glycemic control, and this does not have to be within the diabetes population, it could be other populations. And of course, we can think of real-time interventions as well, where if we have a mobile app that has CGM data, then maybe we want to provide some suggestions. If the glucose rise, maybe you should go for a walk or you take insulin, depending on the person. So this is just some examples, again, not an exhaustive list. So when you want to use this data, how would you summarize it? And this is where there's a lot of CGM-based metrics of glycemic control. This is an older paper, but I still recommend it because I think it summarizes a lot of the metrics from the literature by an expert in the area. And one thing that is happening in the field is that since that paper, there are many more metrics that are continue to be developed and proposed. Just recently, someone wrote me that they have yet another metric. And I think it's really easy to get overwhelmed by the amount of metrics that exist. So today I'm going to try to give you some guidelines on what are those metrics, what are the traditional ones and less traditional ones. And in our case, our package can compute, I think, the most exhaustive list of metrics that I know of because we just decided to implement them all. And it has been recently used to provide reference values for what this metrics should look like in the non-diabetic individuals. So what are the pros and cons of the metrics in general? So different metrics capture different aspects of glycemic control. There are many software packages that exist. Iglu that I'm presenting is obviously one of them, but there are others. There's a nice review paper that you can look at. There are packages in Python, there are packages in MATLAB, and generally packages agree with each other in terms of how they compute the metrics. And there are community activities within CGM to build consensus, which separates it from, for example, accelerometry and actigraphy, where consensus, as far as I know, is harder to reach. And in particular, there is consensus papers regarding CGM metrics that should be used as endpoints for clinical trials. There's also a lot of disadvantages. So a lot of this consensus and metrics are primarily based for type 1 diabetes population. So as we start studying different populations, maybe we're interested in gestational diabetes, or we're interested in patients who develop prediabetes, or whatever that may be, it's not immediately clear that those metrics are the optimal ones. Sometimes the metrics are selected based on interpretability. So some of them, it's very easy to explain to the patient. It's very easy to explain to the provider. maybe they don't provide us with the most power to detect associations that we're interested in. Because I did a lot of work on the CGM software and metrics computation, I can attest to you that how some of the more complex metrics translate into automatic algorithms can vary from software to software. So in some sense, when you select a more complex metric, you also select a software because it can produce something different. And metrics do not fully account for richness of the data, which is something that I would talk a little bit more towards the end. I have a sort of like an opinion paper on this if you want to see more discussion on the metrics pros and cons. There are example data sets that I'm going to use. So those two are public data. They're both coming with the iglu package. This first one is the one that's also pre-uploaded in the Shiny app. They're subjects with type 2 diabetes not on insulin therapy, and there's some other data sets that are also public that you can look at. And in general, I'm sort of given a very broad introduction, but we have a package website, we have papers, we have some specialized vignettes. So depending on what is of interest to you, there is more information out there. All right, so the first thing I'm going to start with, like whenever you do the CGM data analysis, there is this question, how much data do you need? And this consensus paper that I alluded to generally suggests that 2 weeks of data with at least 70% non-missing is a typical standard for outpatient CGM settings. We have a work under preparation. It's not submitted yet, but we had a poster at CDI symposium, and we would have a poster at the metric symposium that Victoria alluded to in the beginning, where if you want to represent 3 months of glycemic exposure, we really suggest that you need at least 1 month of data, that 2 weeks may not be enough. Depending on what you're studying, maybe you're only interested in 2 weeks, and then that's a different conversation. So the first thing you kind of need to do with your data is check how much data is missing and how much data you have. And within iglu, we have an active percent function that basically for each subject tells you the total number of days that the measurements represent, and then how much of this was non-missing. So based on those two numbers, you can create a filter for the data availability and only look at the data that where you know you have enough days. All right. The other thing I recommend right away is to visualize your data. That may not always be possible if you have like thousands of subjects, but for curated clinical studies, that's typically possible. So this is the 5 subject data that we have in the package. And right away, what you can see from this visuals is that some of them run obviously higher than the other. Some subjects have a larger missing data gap. Maybe they haven't reapplied the meter right away. And that kind of gives you some initial information on the data structure and what it looks like. This is a very typical representation where you do a time series and the red lines again indicate 70 to 180. All right. There are other ways to visualize it. One way we do in the package is what's called a lasagna plot. So this using the color scheme that is commonly adopted with CGM data, where green represents in range, orange represents hyperglycemia or high, and red represents hypoglycemia or low. So rather than having a time series plot for this one subject, you can have different days representing horizontally, and then the color is representing the glucose values with gray indicating missingness. So in this case, you can see that 0 to 6 a.m. is where more of the lows happen, although occasionally there are lows in other time periods. So that's just a different temporal resolution to look at the data more closely. For this lasagna representation, you can also order it by time, and that creates kind of overall trends. So you can see that this yellow picture emerges that basically tells you that there's usually some excursions around the afternoon time, and there is lower periods during the nighttime, as you would expect. So that can provide another nice explorative way to assess data on a subject level. So once you visualize the data and have enough filtering for data availability, what are some of the common summaries you can look at? And I'm going to start with a list that has been determined to be the consensus CGM metrics based on this international consensus statement. So these metrics include mean glucose, GMI, which is a glucose management indicator, various time and ranges, measure variability, glucose risk index, and glycemic episodes. And I'm going to go through these metrics one by one. So the mean glucose is the simplest. This is just taking the average glucose over all the period that is available. And here I'm illustrating it side by side with the data. So you kind of have an idea. Subject 2 seems like they run the highest and they have the mean of 218 milligrams per deciliter. And then subject 1 seems to be the lowest, close to subject 4, and they have the mean of 124 and 130 milligrams per deciliter respectively. All right. GMI is actually a deterministic transformation of the mean. So what this means is that you don't need both. You only need one, either mean or the GMI. The reason that GMI exists is that there was a desire to put the mean glucose on the level of HbA1c measurements because HbA1c has been used for really long periods of time. And basically the general guidelines is that A1c of 5.7 to 6.4 is pre-diabetes, above 6.5 is diabetes. And usually the treatment goal is to keep it within the 7. So by translating mean to the GMI, you kind of can now think of these values in the same way as you would think of the HbA1c values. Any questions so far, by the way? Let me just pause. Okay. So time in range is the most common and accepted metric as a treatment target. So the standard thresholds are 70 to 180. And basically what it does is calculate the percentage of time the person spent within this range. So in this case, you can see that subject 1 had 91% of time within the range, whereas subject 2 has only 26% of time within the range. Typically, the goal is to be at least 70% in range for people with diabetes. And just as a side note, for subjects who don't have diabetes, they're not always 100% in range, but they usually have time in range about 95%. The visuals of the plot allows you to also look at this time in range for this real red horizontal lines, and one can adjust this range. For example, the tighter range, 70 to 140, is usually recommended when looking at the diabetes within pregnancy because a tighter control is desired in those cases. Generally speaking, when we think of the glycemic threshold, so 70 to 180 is what I called in range or normal glycemia. Hyper corresponds to high glucose levels. It's often subdivided into level 1 and level 2 using a fixed 250 milligrams per deciliter range. And the hyper or low glucose is also typically subdivided into level 1 and level 2 using 54 milligrams per deciliter range. This color scheme is an accepted color scheme used by manufacturers of CGM devices, by the apps, and so I'm also adjusting it here. So basically, if you look across the thresholds, it gives you a 5-number summary that sums to 100% and tells you the percent of time a person spent within each range. And sometimes level 1 and 2 are combined, in which case you just have hyper in range and hypo. In iglu, you can plot these ranges as I illustrated before, and you can also create this bar plot with just a few commands. In this case, I'm telling you that the subject 5 over here, they have no time below range, so they have no hypoglycemia, but they have some time at the hyperglycemia level 1 and some time in hypoglycemia level 2. So you can kind of have a visual representation on the bar plot representation at the same time. And of course, these ranges can be adjusted depending on the research question. So within the software, you can always adjust this default threshold to any threshold that you may be interested in. And of course, the fixed thresholds are very common. We started questioning, and in general, I question whether these thresholds are optimal for all different populations that we may study. So we have a recent more methodological work where we propose data-driven unsupervised thresholds. So basically, if you have a specific population that you're interested in and you have CGM data for that population, we can help you determine what thresholds may be optimal for that particular data set. Maybe it's not the fixed one. This functionality is not yet on iglu, but we do have a public open code over here, and we have a corresponding preprint. And what I'm showing you here, there's graphs representing on the left, people without diabetes, and on the right, people with type 1 diabetes. Obviously, they're going to have very different CGM data. Each of the vertical lines is a bar plot separated into just 3 areas. This is according to the traditional thresholds. This is according to the data-driven thresholds as determined by our method. And basically, what I'm trying to illustrate is that doing data-driven thresholds can give you more discriminatory power. So in this case, we can perfectly separate a person with type 1 diabetes from a person without based on the free number summaries. And the separation with traditional thresholds is a little bit more ambiguous. All right, the next metric is a coefficient of variation. It's basically a global measure of glycemic variability. It's not the only one, but it is a consensus one. And typically it's evaluated whether it's above 36% or below. Above is considered bad, below is considered good. So from this perspective, all 5 subjects here meet the treatment target of being below 36. Ambulatory glucose profile, or AGP. Oh, sorry, I did this again. I'll try to be more careful. Here we go. So ambulatory glucose profile is a typical assessment. So anyone who wears a unblinded CGM and have an app, they can download their profile as AGP. And it's basically a visual summary that contains all the consensus metrics. So it tells you the start time, the end time, duration, how much non-missing data there was. It tells you average glucose management indicator that we talked about, that is just a translation of average into the A1C scale, and the glucose variability as measured by CV. And then it has the bar plot corresponding to the ranges of the fixed thresholds. Additionally, it gives you a visual representation of the average profile. So again, you can see that across days, this particular subject tends to have a larger values in the afternoon, probably when they do meal intake, and lower values during the night. GRI is another one of the consensus metrics. That's a more recent one. It stands for Glucose Risk Index. It's based on this paper. All the yellow ones are clickable, by the way, so you can always go to the reference, where they asked a lot of clinicians to rank CGM profiles based on the severity, and then they try to come up with a one number summary that would align as close as possible to the rankings produced by the clinicians. So this summary is a linear combination of hypoglycemia scores in level 1 and level 2, and hyperglycemia scores in level 1 and level 2. It's a maximum of 100%. 0 means you are in range 100%. So 0 is good, 100% is bad. So based on this measure, subject 4 and subject 1 will rate the most favorably in terms of the glycemic control. Subject 2 will be the least favorable. And finally, glycemic episodes. So when we talk about the episodes, we talk about the levels again, but it's the levels that last for at least 15 minutes. So high glucose level 1 means that the subject stays over 180 for at least 15 minutes. And then to trigger the end of the episode, they have to come down below 180 for at least 15 minutes. So it looks at the prolonged stay within a certain period. Similarly for level 2, and similarly if you go to the hypoglycemia. This is where episodes in general difficult or more difficult to compute, and they're a little bit more sensitive to the measurement frequency. For example, for Dexcom G6 and G7 that do 5-minute measurement frequency, you basically need 3 consecutive readings to trigger an episode. Freestyle Libre, depending on which one you get, could be 1 minute. Typically, it's agglomerated at 5 minutes. Older models were 15 minutes. So that's where episodes may differ more across different meters with different measurement frequency. In the iglu, episodes can be automatically calculated with one function. There is also a tab on the Shiny app. And basically what it does, it calculates episodes of different levels, extended, non-extended. It gives you average episodes per day, average duration, total episodes, basically anything you want to know about the episodes, it will give you. I do want to give a warning is that interpreting episodes is highly non-trivial. We have, I think, yeah, we have a paper that I'm gonna reference on the next slide, but just to illustrate the difficulty, this is an example profile where the 2 horizontal lines correspond to the episodes for 180 and 250. And basically, according to the definition, what happens is once you go up in this case, this person stays up for a really long time. So from the definition, there's only one level 1 episode, but it happens to be very large in duration. However, the deviations above 250 are more intermittent. So that triggers, by the definition, 3 level 2 episodes, and they are all part of level 1. And the same logic is applied to hypoglycemic episodes. So the basic warning is that I'm not sure how different software compute the episodes. I know how iglu compute the episodes, and this is how it does it. And when you look at the episodes, you couldn't just pick the level like that suits your needs. I think you should look at both levels at the same time, and you should definitely look at the duration as well. There is a numeric output you can do with iglu directly to give you all of this episode information. And for more discussion on what are some of the challenges in computing episodes, including what to do when you have missing data, we have a recent paper that I'm listing right here. All right. If you want all consensus metrics at once, there's also a function that does all of that, which includes active percent. So that's where you can change your data availability statement. And then it includes all the consensus metrics that we talked about. So to summarize, if you just look at the consensus metrics, this is the list according to the International Consensus paper. If you have to pick just one, I would say that time and range is the first and most common default standard. That's the one I would start with. If you want a visual for a particular person, this is where ambulatory glucose profile or AGP summarizes many of these metrics in one place and gives the visual representation. Any questions so far?
Hey, Irina, I have a
Or,
question.
yeah.
So a lot of the metrics that you're looking at look at the big picture. But do you have functions in Igloo to look at more event-based patterns?
Well, this
Like,
would be events. Episode will be events, right? So this episode's function will automatically determine where all of these things happen. It will count how many of them. It will count the average duration and things like that. There are some other metrics as well that are more local that I'm going to talk about. And then there's sort of approaches outside of metrics.
I guess what I was trying to ask is events from other sources of data. So let's say that you are also looking at smartwatch data and looking at HRV or just really high spikes in stress, and then you want to see what glucose does during those episodes.
I mean, that means you would have to do a little bit of coding because you can always subset glucose, right, to those events. But if
Mhm.
those events are happening from other devices, that means you need the functionality to upload data from that device in addition to CGM and then determine the times that you are interested in.
Mhm.
So from CGM data alone, we can identify events like episodes, and then there is another type I show you. If the events come from a different source, that means you'll have to load the different source, or you need to tell iglu what are the times that you want to look at. Like, for example, it's not on the slides, but we do have a functionality to do meal times and postprandial curve metrics. So this will be an illustration where you will tell me what the meal times are. And then iglu would automatically look into the CGM data associated with those meal times and summarize metrics for the postprandial glucose curves. Um, I'm not sure if that's
Mhm.
close to what you had in mind, but
Yep, that's it. Thank you.
yeah. Yeah. Thank you for your question. Yeah, so this is actually a great sideway. So we talked about the common summaries, but you can do a lot more metrics. So this is a heat map of all of the iGlu metrics on 19 subjects. So metrics come vertically, subjects are horizontally. Heat map allows to cluster them based on the metrics that are most similar. So this is a visual way where on your data, you can check what are the metrics that provide similar information, what are the metrics that are different. For example, on here, you can see a group of metrics. I'm gonna like pay attention to this third group, and they all have hyper or below in them. So basically that tells you that all of those metrics trying to get at hypoglycemia in a different way, which means for your particular data set, maybe I will just pick one of those that I understand the best or have the most scientific meaning. I don't want to use all of them because they're going to give me repeated information. Similarly, you can see the sludge group over here, which all have hyper in them, which suggests that this is really trying to get at people who are very hyper. And similarly, you can pick one metric from here based on your understanding of the metric or the scientific rationale. Maybe you don't want all of them because they're capturing similar things. So some of these metrics, there's a lot of variability measures. There's all of this glucose variability between days within time points. They're all very highly correlated, but you can get them all with this SD measures function. You can also get a more like episode-based variability, but where episodes are not defined based on the thresholds, but on the automatic glycemic excursion identification. So there is this metric called MAGE, which is the mean amplitude of glycemic excursions. And basically what it does automatic determination of peaks and nadirs within the CGM profile. It then characterizes the height of all of those excursions, and it can return the average height. Although we also have a functionality to return the height for the individual excursions if desired. So that's more excursion-based analysis that is not dependent on the thresholds. And this is just what it does for the subjects in our study. And you can see the fifth one here has the largest value. So that's basically average excursion size of 142 milligrams per deciliter. That's pretty high. And this is the data, so you can kind of visually see what it does. So it said that subject 5 had the largest excursion magnitude, and you can kind of see that this is true. They have the largest deviation in terms of where they start and where they end over those excursions. Another one is the standard deviation of rate of change. This is more local variability measure. So the idea is that you look at the difference in glucose values within a small time period, like 15 minutes, and you look at the standard deviation of those, which is going to symmetrize the profile. So you go up, you go down. So your average of deviation is going to be 0. And basically what you look at is the spread. So the higher is this variability, the faster are the fluctuations, which is considered to be better to not fluctuate too much. And then you can do this again, not visually, but numerically. And generally, there's a lot more metrics you can compute. Those are the ones that I wanted to highlight that may be of interest. We have a website documentation for reference for other metrics that have been proposed. And again, this heat map implementation, the metrics clustering can give you an idea on your particular data set. What are the metrics that provide complementary value? What are the metrics that may be redundant? I do want to make a note on accuracy and data processing. So a lot of times when I have CGM data from curated data sets, we use it as is. We now have a lot of cloud-based data. We have data in research data warehouse, and this may require additional processing. So this is where we have data where you have a duplication. When you look at this particular figure, there's a lot of overlap and it's really not clear what is going on. And some investigation shows us that there is a duplicated profiles. Sometimes it's a time shift, like you can see over here. Sometimes the pattern is really not clear. So if you're working on a more messy data, well, you should process it first. You should try to remove the duplication. And we have one particular algorithm that will do this automatically so that your metrics quality is maintained. Um, if you are interested in how this works within Michigan Medicine, so we actually have all metrics calculated by iglu, and we did duplication correction with my collaborator Joyce Lee. And so CDI, Informatics and Clinical Research Innovation Services, they provide access to this data. And here is the slide from them that you can use if you are interested in getting access to this metrics and this data from Michigan Medicine. All right, and I think I have 5 minutes, perfect. So I've talked a lot about the metrics, and now I'm gonna highlight what is called CGM Data Analysis 2.0. This is an opinion that just came out with a lot of people that probably some of you can recognize. And basically, this is the field thinking of what happening next and where are we going beyond the metrics. And I'm gonna highlight some of the things here. One is that article actually features lasagna plots that are made by our package iglu. And this is the idea that looking at the temporal patterns visually is kind of the next steps. We don't want to look just globally, what is the time and range, but maybe we want to think about how it changes from night into day and what times of day it's most affected. Looking at it from more statistical perspective, oh, sorry, it did it again. Here we go. Statistical perspective is functional data analysis approaches where we can align the data by time. With CGM, it's really hard to align by 24-hour period, but what we did before is aligning by sleep time. You can also align by the meal time, especially if you have a planned study where you know the time of the meals. So in this case, we aligned it with actigraphy data where we used actigraphy to estimate the time of sleep for each of the subjects, which is in blue. And then we extracted all of the sleep times, which we can now align by the time of sleep. So in this case, each of the figures represent one of the person. Time 0 is estimated time of the sleep onset, and then it goes 7 hours into the sleep. Prior to working with this data, I always naively thought that all people just go down when they sleep. On average, that is the case. That is not universally the case. These are people with type 2 diabetes that are not on insulin. And you can see that there is high variability. Here we had roughly 10 sleep periods per each person, and we displayed 7 hours. But by aligning by this time, you can now start thinking both on what the variation with respect to the time, but you can also look at the time-related associations. For example, here, what we did is we looked at the effect of biguanide, which is an oral medication. And what you see here is that we show that the effect is roughly similar across the period of sleep. So there's association of 10 milligrams per deciliter glucose reduction, but maybe it's a little bit stronger in the middle of the sleep period rather than in the beginning. And then in this context, we also looked at the subjects with obstructive sleep apnea or ASA and showed that there was association with the severity of RSA and higher glucose levels during the night. And here are some of the references for the papers where we use this FDA approaches for CGM modeling. The next one is the distributional approach, where basically you don't align by time, but you try to do a threshold independent representation. So we talked about how the standard thresholds are 54, 70, 180 to 50. They may not generalize to all the populations or be the best. So in this case, we still collapse across the time, but we keep all the individual measurements. So we get the whole distribution of the glucose values. And then we can look at how different covariates affect the full distribution rather than just the threshold. So in this case, for example, these are two density functions corresponding to the drug sulfonylurea and other oral diabetes medication, where we show that people who are on the drug in general have a wider density, meaning they exhibit higher variability in their glucose levels compared to the people who are not on the drug. And there's some other covariates effect that we found. So this has a lot of potential for looking at the whole distribution that is threshold independent. You can use this whole distribution for patient clustering and treatment effect estimation and other context, giving you more power compared to fixing thresholds at a particular level. And finally, we all know that AI is here. And of course, deep learning and AI have been used in the context of glucose primarily for the prediction. So here I'm illustrating one of our works where basically, given the past, we're trying to predict 1 hour into the future. And rather than just giving a prediction that is just a line, we're trying to do an uncertainty that is associated with that prediction. And this could be a prediction that is unimodal. This could be a prediction that is bimodal. And what we also done within the space is we have a public repository of curated data sets, CGM data sets with machine learning models that one can benchmark the model performance against this public data using standardized processing tasks. And over here, just to summarize, so what I've presented today are some current recommended processing pipeline, which is quality checks, data visualizations, data availability filtering, how much data you have per certain patient, what are the consensus metrics? This is where I would probably start. And then what are some other metrics you may be looking at, and how you can use this heat map to try to select the metrics for your data and your research questions. And I think where the field is moving, or enhancements, is trying to move away from fixed thresholds. So we had sort of two approaches. If you like the interpretability of threshold, maybe just adjusting the threshold choice for your data set, but trying to look at the whole distribution. Also looking at the temporal alignment, either along sleep time or meal time. And then, of course, a lot of AI and machine learning in the context of glucose forecasting. And I'm going to stop here. Thank you very much. And I'm happy to take any questions.